All right, calculus. Calculus is really three big ideas: limits, derivatives, and integrals. And the fact is that we will not be looking at those for a while. We'll be focusing on limits. And the concept of a limit is very important. It's fundamental to the development of calculus. But the fact is that if I want to give you an idea of what a limit is, I'm going to give you this idea right now. I take the number 1/2 and I divide it by 2 and add it on. So 1/2 plus 1/4. Let's keep a running total. We started with a half. And if we added a 1/4 to it, that's 3/4. Let's take half of that 1/4, which would be an 1/8. Well, now I have 3/4 plus an 1/8 is 7/8. If I add on half of that, I add on a 1/16. And now I get 15/16. If I add on, let's see, half of a 1/16 is a 32nd. And I would get 31 32nds. If I added on half of that again, I would get 63 64ths. Now, if you notice, this is really close to 1. So if you continue to add this, as you add more and more and more and more numbers together like that, you're getting really close to 1. You're getting really close to 1. And so as we see this notation, limit of f of x is equal to L as x approaches a, what it means is this. The limit of a function, that's this guy right here. The limit of the function as x approaches a, that's this guy right here. The limit of the function as x approaches a is L. And what that means for us is as x values get closer to a being some number, then the y values get closer to another number. And we call that number L, or the limit. And we're going to give you some examples here. We've got some very basic examples to start. This graph looks something like that, where this is at 3. And the question is, what is the limit of the function as x gets closer to 2? So 1, 2. So as we plug in 2, what are the y values getting closer towards? So I'm going to examine this a couple ways. The first way I'm going to examine it is I'm going to look at the graph. 0.5x squared minus x plus 3. As I consider that graph, okay, I consider that graph, I'm going to zoom standard, and I'm going to trace. And as I trace, I'm going to bring x so that it's closer to 2. And I look at the y values. Y values are getting bigger. Got 2.5. Okay, I got 1.0, still got 2.5 there. 1.27, got 2.5. 1.4, I got 2.6. 1.7, I got 2.7. 1.9, I've got 2.9. So I'm getting x closer to 2. What's happening to y? Oh, look, I just went over the other side. Now I've got 2.1 and it's 3.1. So as x gets really close to 2, y gets really close to, well, it looks like it might be somewhere around 3. If we check the table, that's another way to do it. I'm going to go ahead and plug in numbers that are close to 2. For example, 1.5, that's close to 2. Or 1.9, that's close to 2. Or 1.99, that's a lot closer to 2. In fact, 1.9999, that's really close to 2. And you can see that as the x values get really close to 2, the y values get really close to 3. We could go from the other side. So right now we kind of approached x from that side. Now we could approach it from this side. So I could take numbers just a little bit bigger than 2, like 2.1 or 2.01 or 2.0001. And you can see that those values are getting closer to 3. In fact, if you plug in 2, you actually get 3. But I want to be clear, it's not what you plug in, it's what it's getting close to. It's a big difference. Now, in this situation, it does happen that the limit is the same as what you get when you plug in 2. If I plug in 2 for x, I do come out with 3, and that happens to be the limit. That is not always the case, though. Consider this example, square root of x plus 4. We're going to take the limit as x goes to 0. Well, the square root of x plus 4 is a graph that looks, let's see, it's shifted back 4 units. Looks like that. As you consider the graph, as we approach x from the left, looks like the outputs are getting really close to 2. How do I know that? Because if you plug in 0, you get the square root of 4, which is 2. Looks like I'm getting close to 2. If you approach x from the right by looking at the graph, it looks like you're also getting close to 2. So in fact, the limit is 2. We get 9 minus 9 divided by 0, or 3 minus 3. You get 0 over 0. What is 0 over 0? 0 over 0 is a huge question. It's a question we have in calculus all the time. Some people say it's 1. Some people say it's 0. Usually both of those are wrong. We have to figure it out. It requires very close examination. Well, let's see what the graph looks like. I go into y equals, and I'm going to put parentheses around the x squared minus 3x. I'm going to divide that by parentheses x minus 3. And when I do that, I'm going to zoom standard, and I'm going to look at the graph. It basically looks like that. Now I'm going to let you in on a little secret here. That's what the graph looks like. If you look at it, maybe you notice if you factored an x out of the top, you would get an x minus 3. So what does that mean? That means that at 3 is where you have a hole. Watch, if I zoom as a decimal number 4, watch what happens with my graph. Whoop, you see right up there at the top? See right up there at the top, it's got a hole. It's got a gap. Right there. At 3. Now, at 3, that's where it gets crossed off. What's left over? That's what the graph wants to look like. So the graph looks like y equals x. It's just got a hole at 3. So what's the limit? If you plug in 3, you don't get any value. But as we approach from the left, looks like the output's getting close to 3. As you approach from the right, looks like the output is getting close to 3. In fact, if you looked at the table, if we get close to 3, like 2.5, 2.9, 2.99, you can see the values are getting really close to 3. If you try the other side, you try like 3.1, 3.001, 3.00001, and you can see that you are in fact getting values very close. So sometimes you can't just plug it in. You have to analyze the graph further. This is one of my favorites. If we try plugging in 0, you get sine of 1 divided by 0. You know 1 divided by 0 is undefined, so that doesn't work. I go into y equals, I'm going to look at this graph. I do sine of 1 divided by x. Mode, make sure I'm working in radians, and I am. I'm going to zoom 6 for zooming standard. And I'm going to look at the resulting graph. The resulting graph looks like something like that. It's really tough to tell as x goes to 0, what does the y value head towards? That's very difficult to be able to tell. So I'm going to zoom in, and I'm going to see what happens. Zoom 2. I press enter there. Ooh. That's kind of interesting. Bounces up and down there. I'm going to zoom in further. Whoa. So maybe graph more like that. There's a lot of crazy stuff that happens there. Zoom number 2 again. Let's see if we can figure this out. Wow. As x goes to 0, are you clear what happens with the y value? I'm not. I'll zoom in again. Well, that's ridiculous. Every time I zoom in, the behavior just seems to jump up and down. In fact, it's like, what does the graph look like? And the graph looks a barcode. In fact, it's called the barcode function. And we can't ever tell as x goes to 0 what happens. In fact, if you look at the table, like 0.1, 0.01, 0.001. He was at negative 0.54, then negative 0.5, but then jumps up to 0.82, 0.0001. And then jumps back down to negative 0.3, 0.00001. And then 0.03. In fact, this limit does not exist. It never comes in on one number. Sometimes what we need to do is we need to approaching functions from the left as well as from the right. This is the notation for a left-hand limit. Suppose it says limit as x approaches 4 from the negative of the function. What that means is you're going to type in values like 3.5, 3.9, 3.99, values that are to the left of 4. Looks like this, say the limit as x goes to 3 from the positive of the function. What that means you're going to approach it from the right. So it'll be like 3.5, 3.1, 3.01, 3.001. Different when you approach things. We want to do two things today. We want to be able to look at limits by looking at a graph, and we want to be able to look at limits. So this one says the limit as x approaches negative 4, so we're approaching negative 4, and it means that we're approaching from the left. So as you go from the left, you can see that the output is getting very close to 3. This one says approach it from the right. As you approach it from the right, you can see that the output is getting very close to negative 2. Now, the truth is that there's no closed circle here. You don't have to have a closed circle in order for the limit to exist. Again, it's not what is f of negative 4. If it said what is f of negative 4, that would be, in fact, 3. But it's saying the limit, what are the values getting very close to? We have this one, limit as x goes to negative 1. From the left, we go to 4. From the right, we go to 4. So you can see in both situations, whether it be from the left or the right, it's 4. Look at this one. It says 2 from the left. I get negative 1. I go and I get 5. This says 2. If it doesn't have a left or a right, that means it's a two-sided limit. In order to see if a two-sided limit exists, the rule is it must be the same from the left as it is from the right. And in this situation, negative 1 and 5 are not the same, so this limit does not exist. We'll get back to letter H in a second. Just flip it over. Formal definition of a limit. The limit as x goes to a of the function is equal to f. Only if the limit as x goes to a from the left is the same as the limit as x goes to a from the right, which is the limit. If the left side and the right side are the same, then the limit exists. So, if we check back to letter H, the limit as x goes to 4. So that doesn't have a plus or minus on the top, so that means a two-sided limit. So we check it from the left, and we get 2. We check it from the right, and we get 2. Those are the same, so the limit is definitively 2. Notice you don't have it's undefined. There is no f of 4, but there is. Instead of looking at a graph, let's use our table. We're going to go to y minus 4 divided by parentheses x minus 2. zoom, I'm sorry, table, and it says to approach 2. So I'm going to approach it from the left. So I'm going to type in values like 1.5, 1.9, 1.99, 1.999, and we would say that it looks like it's approaching 4. We can't say that for sure unless we approach it from the right. So if we approach it from the right, we try values like 2.5, 2.1, 2.01, 2.0001. And you can see that in both situations, you are in fact approaching a value of 4. Look at the next one. Sine of x over x. I go into y equals sine of x divided by x. And when I go into my table, I'm going to approach 0. Well, 0 from the left would be negative 1, negative 0.1, negative 0.01, negative 0.0001. And you can see that those values seem to be getting very close to 1. Now, I don't know for sure if it's 1 until I check the right side. I'd try 0.5, try 0.1, try 0.01, try 0.001. And you can see as you try those, in fact, it looks like those values are getting very close to 1. So it is 1. Just about done here. The graph of 1 over x to the 4th looks like this. Vertical asymptote right here. And the question is, what is the limit as x goes to 0? Well, as x goes to 0 from the left, you can see that the values get extraordinarily large. In fact, they head up towards infinity. And as x tends towards 0 from the right, it also heads up towards infinity. Those are the same, so the limit is infinity. We can use infinity as a limit. The next graph is undefined at 1. And if we checked on the calculator, we would see that the graph, in fact, looks like this. There we have it. The limit as x goes to 1, from the left, you can see that you head down towards negative infinity. As you head to 1 from the right, the graph goes up towards positive infinity. Those are not the same, therefore the limit does not exist. And it raises an interesting scenario. In both these situations, we have what we call vertical asymptotes. When you have limits that involve infinity, infinite limits, limit as x goes to a of f of x is equal to infinity, in plain terms, as x gets closer to a, y gets super big. If x equals a is an equation for a vertical asymptote, then we have the limit as x approaches a of f of x is either equal to infinity or negative infinity, or it does not exist. Okay? If there's a vertical asymptote, then one of the two are true. So if you have a limit that involves infinity, you should be able to identify the vertical asymptote. The last question says, identify the equations for the vertical asymptotes. In this situation, the vertical asymptote is x is equal to 0. And in this situation, the vertical asymptote is x is equal to 1. If you notice, that's what it's approaching, and that's what gives you 0 in the denominator. Okay, that was a good, actually it was shorter than the first video I did. We saved you a little bit of time there. I hope you're learning a lot. Get your questions ready. Let's go over them in class together.